All right, ready to dive into some seriously mind-bending physics.
Always up for that.
Today we're tackling Einstein's special relativity.
Ah, the cornerstone of modern physics. Where are we starting?
With a question.
Okay, shoot.
What if I told you we could understand it through something as simple as, well, waves?
Waves, like on the ocean.
Exactly. We're diving into this cool piece called Puzzle Piece 3. What's special about special relativity?
Intriguing title. Where's it from?
Website called The Red Pill. They explore some really out there physics concepts, and
But we're focusing on the wave analogy, right?
yeah, it's all about visualizing time dilation, length contraction, things that usually make your head spin.
I'm all for a good visualization.
So picture this. You're on a boat, right?
Okay, I'm on a boat.
You drop a stick into the water, those ripples that spread out, those are our waves.
All right, I'm seeing it. Classic wave action.
Now the boat starts moving. What happens to the waves?
Well, the ones in front get closer together, the ones behind spread out.
Exactly. That's the heart of it, that change based on relative motion.
So how does this relate to something like, say, time dilation?
Okay, so time dilation.
Yeah.
It's the idea that time itself can slow down.
Right. The faster you move, the slower time passes relative to someone standing still.
Our source uses this great example of a water clock to illustrate this.
Water clock. Okay. I'm intrigued.
Imagine a frame, a bell at one end.
Which is simple enough.
A wave travels the length of the frame, hits the bell. That's one tick of our clock.
Gotcha. So the wave is like the ticking hand.
Exactly. Now, if the boat's stationary, the wave goes straight to the bell. Short trip.
Yeah, a nice quick tick.
But when the boat's moving, that wave has to travel diagonally to catch up to the bell, a longer path.
So that tick, that same wave traveling, takes longer.
Boom. Time dilation.
Wow, it's like time itself is being stretched out.
And it gets even wilder.
Wilder. How so?
Some theories suggest that matter itself, everything around us, might actually be made of waves.
Okay, now that is a wild concept. Matter as waves.
So if we're made of these waves moving through some kind of medium,
Then wouldn't our own internal clocks, our very experience of time, be subject to these same effects?
exactly.
Wow.
Mind blown yet.
Just getting started, I think.
Our experience of time, it's not this fixed thing we think it is, you know?
Right, it's relative. It can be warped, especially at high speeds.
And get this wave idea, it messes with length too.
Length, you mean like length contraction?
Exactly. Remember that stick we were dipping in the water?
Yeah, creating our waves.
Our source, they point out something really cool. When the boat's moving and you drop the stick,
Okay, picturing it. Boat's cruising, stick goes plop.
the distance between those wave crests, it actually looks different depending on where you are.
Oh, right, like bunched up at the front, spread out at the back.
Yeah. Now, imagine those wave crests are markings on a ruler.
Okay, a ruler made of waves. I'm following.
If we're made of waves, moving through this medium, our own ruler would shrink in the direction we're going.
Whoa, hold on. So as we move faster,
Our measuring stick gets shorter.
yeah.
Yeah.
We wouldn't even know it, would we?
Exactly. It'd be like our perception of distance itself is changing.
That's wild. So, like, if you're flying through space at near light speed,
Everything ahead of you seems squished, but to you, it looks normal.
it's like the universe is warping around you based on how fast you're going.
This is what blows my mind about relativity. There's no one true measurement. It's all relative.
And this wave analogy, it's not just some random example, is it? It ties into so much.
You're right. Think about the Doppler effect.
The siren sound changing as it passes by.
Yeah, that's waves messing with our perception too.
Higher pitch as it comes towards you, lower as it goes away.
Because the sound waves themselves are getting squished or stretched.
Just like our ruler, our time, it's all connected.
It's like this whole web of weirdness all stemming from how waves behave.
So cool, though.
It really makes you think, doesn't it? Like,
Yeah.
our brains want to see time and space as these fixed things.
Total constants, right? Our bedrock of reality.
But this wave analogy, it's like, whoa, maybe everything's way more fluid than we realize.
Exactly. If our very tools for measuring, for even perceiving reality, are subject to change.
Then what is constant? What's real? It's like, whoa, dude.
I know, right? It's these kinds of questions that keep physicists up at night.
And Einstein, he was all about thought experiments to wrap his head around this stuff.
And that's the beauty of this wave analogy. We get to do thought experiments, too.
It takes something as complex as special relativity and makes it, well, not easy, but
Approachable.
yeah. We could visualize it, get a feel for it, without drowning in equations.
And that's what good science communication is all about, right? Opening those doors.
Totally. Our goal wasn't to turn everyone into Einstein today, but to spark that curiosity.
That sense of awe when you realize how much you don't know about the universe.
Exactly. Because physics, at its heart, it's not about memorizing formulas.
It's about asking the big questions. What is reality? How does it all work?
And maybe, just maybe, this wave analogy, it's a step towards those answers.
Or at least a step towards asking even better questions.
So as we wrap up, here's something to chew on. If the universe isn't this empty stage, but more like
a vast dynamic ocean of waves, you're saying?
exactly, an ocean where time and space can bend and ripple, what else might we discover? What other seemingly impossible phenomena might suddenly make sense?
That is a thought, isn't it?
Thanks for joining us on this incredible deep dive. Until next time.